Bonjour, welcome to Wahsa Distance Education Center's radio Zoom classes. This is MBF3C, in College Math, and I am teacher Bronwyn Slate. If you'd like to participate live today, you can call the Wahsa studio at 1-800-465-7144 or 4017. Then you can ask me questions. If you'd like to listen on the radio, it's 91.9 FM or on the television at Bell Express View channel 972. You are always welcome to join me live through the Zoom link, which I've sent out to your DECs, and you can also get again from me. Our classes are scheduled Monday through Thursday from 11 to 12 in the morning, and we're now in our 6th week of our 9-week course. At this point, you should be submitting some work for marking. So a reminder of what to submit. The questions marked with the pencil icon are the support questions, and they are not for marking. They're just practice questions. So you decide which ones you need to do and how many of them. If you're understanding a concept, feel free to skip questions. If you need more practice, let me know and I'll send you more practice. The answers are in the back of your booklet, so please check your work to make sure you're on the right track. However, some mistakes have been found, so if something isn't lining up and not making sense, let me know and we can check to see if that's an error that's been missed. The key questions, the ones marked with the key icons, are the ones to submit for marking. So please do all of those questions and show all of your work, all of your thinking, so I can give credit for all of your understanding. If you just give me the final answer, if you're making an error, I don't know where that error is, so I can't help you to learn better for the future, and I also can't give you part marks for the understanding that you do have. A reminder of how to submit your work for marking. There are 3 methods. The first method is to scan and send your work in electronically. So you can scan in your completed work. If you have a smartphone, you can use an iPhone, the Notes app, or the Android Google Drive app if you have an Android phone. If you don't have a smartphone and you just want to take pictures, that's fine too. Or you, of course, can just use an old-fashioned scanner on a printer. Then you can send it to me either through email at studentwork@nnec.on.ca, and then CC it to me, bronwyn.slate@nnec.on.ca, or you can also send it to me through Facebook Messenger at bslatewahsa. Second method is to drop your work off in Lookout. We have an outdoor mailbox at our location 74 Front Street. We're the big red building next to the post office, and there's a small white mailbox next to our side entrance. We continue to work remotely, so it may take me a few days to get your work, but I will mark it and get it back to you as quickly as I can. To hand your work into your DEC. Your DEC can then either send your work through the Express or fax it to 807-737-1732 or toll-free fax 1-800-463-7852. If you have any questions or concerns or struggling with anything, please contact me. My email address is bronwyn.slate, which is spelled BRONWYN.SLATE@nnec.on.ca. You can Facebook me, message me at bslatewahsa. You can call the main office and leave a message for me and I'll return your call. The number is 807-737-1488, or you can call toll free 1-800-667-3703. My office hours are Monday to Friday, 8 a.m. to 2 p.m., and I'll get back to you as soon as I can. You do want to connect with me through social media. My Facebook profile and my YouTube channel are both called bslatewahsa. You can friend me on Facebook and subscribe to my YouTube channel. And then all of our radio Zoom classes I upload them shortly after airing, and then I share them on Facebook and they're uploaded to YouTube, so you can access them there. There's a playlist called our class MBF3C. So all of our lessons so far are there in the same place, really easy to find. And I upload our future lessons there as well. There are also short videos explaining common errors or confusing concepts, things that either we've gone through over our class and I've just sort of narrowed in on that specific topic to sort of give you another approach or just a really focused approach instead of going through the whole lesson, or also things that are common things that people struggle with that aren't taught in our class, but are building blocks, things that you need to understand for our class. So you can go there and check out those videos if you're struggling with anything. If there's anything in particular that you're struggling with and you want me to make a video, let me know and I can do that and then upload it there. Math is an incredible subject, so please set yourself up for success by accessing the videos. Either joining me live through the Zoom, you don't need to ask me questions, but just being able to see the visual is going to help, or watching the replays on YouTube is really going to make most sense. A lot of the things, if you're just listening to me talking, are not going to make sense. It's about organization of information. It's about making connections to the visuals. So it's really would be much harder to just listen to it than see the visuals. If you don't have access to consistent, reliable internet, let me know and I can send you a USB key with a copy of all the lessons that we've done so far so that you can still have access to those videos. All right, we are on day 22 of our course and we're diving into lesson 15, which is creating nets. Our learning goals for today are that at the end of this lesson, you can say, I will be able to use nets to transform two-dimensional drawings into three-dimensional figures. And 2, I will understand the difference between nets, patterns, and plans. Our success criteria are that 1, I can visualize 3D objects and the nets that create them, and 2, I can explain what makes a net, pattern, and a plan. Being able to do that means that you've covered our learning goals. All right, let's do some brain activation and some mental math to get us warmed up. On and on about how I'm not a fan of the Mad Minute math tradition that many of us experienced in elementary school. There's much research done on why this was not beneficial, why this did not help us, did not give us confidence or strategies for dealing with our facts. So instead of doing that drill and kill method, we talk quickly about some strategies that we can use in various situations that are transferable and that are about our comfort with numbers that we can use in multiple different ways. So today's question is 756 divided by 24, and we're using the strategy of multiplying up. So division is not something that most folks are very confident with, and long division has never been something that everyone has felt really like they understand what's going on. So having different strategies for doing division is really important. And so this one, multiplying up, means that we're going to start at our divisor, the number that we're dividing our groups into, and we're going to think about how many groups of those gets us to 756. So I'm just going to think, okay, well, 24 times 10 is equal to 240. Okay, so I haven't got to where I need to be, so I need to do more. So I'm going to say, okay, well, 24 times 20 groups is going to be double that. So that's going to be 480. Okay, so I'm getting closer, but I'm still not there yet. So I'm going to think, okay, 24 times 30 is going to give me 720. Okay, so that's getting me a lot closer than where I was before. So then I'm going to think, okay, I'm just going to say 24 times 31. I'm going to say that's going to be 720, just plus another 24, so 744. Okay, so that's not quite, we're trying to get to 756, so I'm not quite there yet, but I'm getting a lot closer. So 24 times 32 is going to be another 24 more than 744. So that's going to be 768, which we can see is more than our 756. So we know that we don't have, 32 groups is too many, but 31 groups is not enough. So we can, if we're going to try to get closer, we can do, okay, well, it's 124 times 31.5. So I had 24 times 31 was 744. So if I'm only going to do half of my 24 group, so that's going to be 12. So I'm going to add a 12 to 744. So I have 756, which is the amount that we wanted. So we were even able to do decimals in our multiplication based on the logic that we were using. So 756 divided by 24 is 31.5. And that's how you can use the strategy of multiplying up in friendly groups and things that are accessible to you to get to do division. But it might not always work out as easily as this did. This just happened to be that we were able to figure it out exactly, you could just get close and figure out what a remainder would be, and that would be fine too. All right, mine's on. Let's engage in some prior learning to set us up for success for today's lesson. We're going to do a reminder of some geometric shapes, just because that's what we're going to be talking about, to make sure that everybody knows what it is that I'm talking about. The key, one thing to remember though, is that if you need a formula or you aren't sure what a word means, it is fine to look it up. It is completely reasonable that you don't have all of these memorized. If you don't know what a trapezoid is, look it up. If you don't know the difference between a rhombus and a square, look it up. Totally fine. If you don't know the formula for surface area, look it up. It's fine. It isn't expected that we all have all of this information categorized in our brain. Your brain needs to be able to do more things that are more relevant to your life. And that's why we can look it up. We have the access to the internet. There's so much information out there that you don't need to have memorized. It is completely reasonable to look up information that you don't know. It is not shameful. It does not mean that you're not successful. Look up information if you don't remember it. That's fine. So a recap of some two-dimensional shapes. Hopefully many of these are familiar. So we have a circle, which is a round shape that every point is the same distance from the center. We have an oval where it's a round shape, so corners, no straight lines, where every point is not the same distance from the center. It's defined in a slightly different way. We don't need to go to the definition, but it's like a squished circle. A triangle has 3 straight sides and 3 vertices, 3 corners. A square has 4 straight sides that are the same length and 4 corners. The angles of our 4 corners are 90 degrees. A rectangle has 4 straight sides where the opposite sides are parallel each other and the same length. And again, our angles are 90 degrees. A parallelogram, we have 4 straight sides where our opposite sides are the same length and parallel to each other, but now our angles are not 90 degrees. They're different. A trapezoid, we have 4 straight sides and 4 angles. And we have 2 parallel sides and 2 sides that are not parallel. And our side lengths don't have to be the same. A pentagon means that we have 5 sides and 5 corners. They don't have to be, we have a regular pentagon where they are all the same size, but they don't have to be. A hexagon is a shape with 6 sides and 6 corners, 6 vertices. Again, the sides don't have to be the same length. An octagon, we have 8 sides and 8 vertices. Again, the sides don't have to all be the same length. These pentagon, hexagon, and octagon, there are other shapes as well. Many of those we often look at as them having the same length, but they don't have to be. These are called the regular versions. All right, and then we also have 3-dimensional shapes. So we have a cube, and we can look at it in 2 ways. We can look at it so it's solid, or we can look at it such that it's transparent and we can see the front faces and the back faces. So a cube, so a face is just like you think, it's the face of the object. It's the side of the object because it's 3-dimensional. So a cube is a 3-dimensional version of a square. A sphere is a 3-dimensional version of a circle. A rectangular prism is a 3-dimensional version of a rectangle. So you may have 2 of your faces that are opposite may be squares, or they may all be rectangles. And then we have a cone where we have a circle and that goes up to a point to make it 3-dimensional. A rectangular pyramid where all of our faces are triangles. They don't have to be the same type of triangles or the exact same triangles. Some of them are going to be the same, but not all of them. Cylinder, which is where we have a circle, 2 circle faces that are parallel to each other and then are connected with straight sides. A triangular prism, which is when we have 2 faces are triangles and they're connected with rectangle faces. And base pyramid, a square pyramid, where we have a pyramid, so we have triangle faces up to a point, and then the base is a square. And so these things we can look at different angles, and again, we can look at them as solid or transparent, so we can see the back faces as well. It can be a little bit trippy to visualize these, and it also can be hard to draw these. So we're going to use some tools in case you're not great at drawing them. They do not need to be perfect at all. I will not draw perfect ones, definitely. We also want to remember about scale. So scale is the ratio between two sets of measurements. And in scale drawings, the ratio of the measurement of a drawing compared to the measurement of an original subject. So if we are drawing a scale of a house, or we're drawing a picture of a house, like a floor plan, then we're going to draw things to scale. We're not going to actually draw a room that is 10 feet by 12 feet. We're not actually going to draw on a piece of paper 10 feet by 12 feet. That would be ridiculous. We're going to scale it down. We're going to use a scale such that it is representing that, okay, so 1 inch is equal to 1 foot. So then we would draw it to be 10 inches to 12 inches on our piece of paper, so that we could make that, see that visual representation. So here's a visual of that. So here we have a ratio of 1 to 1, where our A and B rectangular prisms are the same. Here we have a ratio of 1 to 2, where our A is still our original size, but B now is doubled in all directions. So our width, our depth, and our height have all been doubled. So it is in scale. It looks exactly the same thing. It just looks like we've zoomed in or we've blown that up to make it bigger. Then ratio 1 to 3, the same thing. Our B is now 3 times in terms of the length, the depth, and the height. And ratio 1 to 4, our B is 4 times the length, the depth, and the height. So it's really important for ratios that you are, or for scale, that you're increasing each dimension by the same amount in order to not skew your information. Okay, so let's explore some new learning. Answering the question, when will I use this in real life? So we are learning how to see the whole picture. In today's lesson and in general, we are looking at parts and we are trying to connect them to figure out everything that's going on in life. We will often have little bits of information or pieces of information, and we need to then extrapolate that. We need to expand that to think about the whole situation. And so we're developing that skill. Nets are all around us. So I have some visuals on here where I have cars, where we have a plan where we can see the distance, the size of this car and the dimensions of it. We see the front view, the back view, the side view, and the top view. That gives us information about what that car. We have a pattern of a dress where we see the sleeve, the front, the back, and the skirt, the front and the back. So that's how we can visualize what that sort of is and how we could make that. And then we also have a net of a little box carrier where you can see how the box is folded up and would be useful to carry something, but then how it's unfolded, it's like a piece of cardboard in my mind, and how it all connects so that we can fold it together and make that box. And that would be a net. So first, let's dive into nets. So nets, this is on page 38 of your IL book, and they are 2D, two-dimensional representations of a three-dimensional, a 3D figure that results when the figure is unfolded. So if we take an object and we were able to unfold it, to break it down and make it flat, that would be a net. When we unfolded, the original figure becomes a flat shape where all the edges meet to keep the net as one piece. So it's still connected, but it's a flat version of what we were, of the 3D object, and it's everything's still connected so we could refold it and it could create what we had it to begin with. So a lot of our 3D objects are created from flat material. So for example, cardboard boxes are a great example. Many of us have to flatten out cardboard boxes, and that we are putting it back into its net. But sheet metal in ductwork is also cut from flat material and then bent to form the object of the duct. So we do this often in various places. All right, I have 2 different visuals that we're just going to look at. So I'm going to link these in our show notes, but we can go to Polypad and we can look at a few 3-dimensional objects that we can look at the nets. There's not as many as I would like, but there's a few. So if you go into the, in the show notes, you can link to this into Mathigon, the Polypad. Again, there is a apps that you can use as well that I'll link in the show notes. And you click over here to all the tiles that you can choose from. We're going to geometry and we're going to 3D solids. So here you can see we have a few different solids. So if we were to take a cube and we can here visualize it, we can see, we can turn this cube around and we can see that it's a closed object, that we have all of the faces are there. And then we can actually unfold it. We can do it ourselves with the slider, and we can see that if we unfolded it, or we can also click this button that says unfold, and then it does it for us. The interesting thing about cubes is that there's more than one net. So we can move these, the faces around, and then we can, if we select it and we can fold the net, we can then see that even though I move that face, we're still able to get a cube. However, not every way that we move the faces is going to work to make a cube. So if I fold it here, this one, we can see when I folded it, it wasn't able to make a cube from that placement that I put that other face. When we folded it together, we don't get a cube. We get an open box of something that could be useful maybe, but it's not going to get us a cube like we had originally. So not every orientation of our 6 faces is going to give us a cube, but there are multiple ways that do. So you may be able to play, you can go into this and play around in terms of folding things up to see what's going to work and what's not. And that can be fun a little bit. All right, so that was a cube, but we can also look, there's all other shapes as well. So here we have a prism. So this prism has a hexagon on its base and it's the top, and then it has rectangles along the side. So then when we unfold that, we can see this would be the net that shows us that all of the sides are attached. So one base is attached to the 6 rectangle sides, and then one of the other base, the other end, is only attached to one of the rectangle sides, because it doesn't make sense that it's attached to multiple of them. It could be attached to any of them. It doesn't have to be just the one that the animation does, but it has to be attached to only one. It can't physically be attached to multiples. And then you see there's various other shapes that you can play with a little bit, and you can see how they are done. And you can move them around and see what happens if you try to move them around to see if you can still make a folded net. Sometimes you're going to get this error message that says this is not a valid polyhedron net. So it means that we can't actually fold this again in a way that would make a shape. All right, so that's one place that you can go in Mathigon. You can play with the nets a little bit to be able to visualize instead of actually, we don't have shapes. So this, that we can actually tangibly hold and move around. But this is a way that you can sort of play a little bit with a few shapes, not all of them, but a few shapes. So that's a good place to sort of understand how nets work. The other place that I'm going to link into the show notes is that there is this GeoBra activity that has a net of a cone, a cube, a square, and a cylinder. So the Polypad doesn't have a net of a cone and a cylinder, which I don't understand, but they don't. So this is where you can go, so you can look at those ones with as well. And so if you click in here, you can again play and see what's going on. So you're given the 3-dimensional object. In the GeoBra, they give you, you can change your height, so you can change how tall your object is, and the radius, you can change how wide your radius is. So that's fun. We don't need to actually look at the formula to calculate this. So this is the surface area. We're not interested in that at this point. We're just sort of playing a little bit with the visualizing it. And then you can use this net and you can open it up, and it shows you when you open it up what it would look like. And then close it. You can press this play button and it actually does it. It opens up the net. It's like cuts it open and flattens it out to see how it would work. And then it folds it back together. So you can do that for a cone, for a cube. Again, it shows you how it opens up all of the faces and how it makes one version of the net. You can then also do it for a square pyramid, So then seeing how the triangle side faces opens up, and then you have a square pyramid, and then you have your 4 triangle faces. And then you can also do the same thing for a cylinder, where you see how you have 2 faces that are circles. And then if you were to cut and open up the part that connects it, you get this big long rectangle. And this one you can play with a little bit. This one's sort of hard to see. It goes really fast. So you can see that this would be the net of a cylinder. So I will link both of those into the show notes so that you can play around with them a little bit to visualize really what's going on with the cylinder. It's something that's really hard, visualizing with nets. It's really hard to just look at a flat surface in your IL booklet or just online, to just look at the 3D object and then try to visualize the net. That is hard. If we were in a classroom, we would actually play with paper and play with objects to physically see what's going on. The next best thing we can do is look at these animations online. So I would strongly encourage you to go and play with those 2 different websites to sort of get a feel of how the nets work. All right, so then also with patterns is our next one that we want to just understand. So patterns are another 2D representation of a 3D object, but this results when the figure is separated into 2 or more individual shapes. So a net, everything is still connected. A pattern, everything can be disconnected. So this is something that we often use in terms of clothing. All of our clothing are based on patterns. And so if you were to take your clothing apart at the seams, if it's sewn together, what you end up with, the clothing that you end up with would be from a pattern. So here is a visual from Polygon, where you can see we have a hexagon and we have 6 triangles that I've rearranged so that they take up the least amount of space. So this, if we were to cut this out of a piece of paper or out of some other sort of material, we're getting less waste because of how we're organized it. So you can also play with that in Polypad again. You can move things around, and so you can make a pattern. I've done that again. It doesn't do it for you, but you can play around with it to see how that pattern could work. And then you can rearrange play with your objects so that you can try to get it back to be the shape that it was before. And then you can see if you can actually make it so that it's back to the 3-dimensional shape if you wanted to. So again, totally a good idea to just go and play with these visuals, these animations, to get a feel for what is going on with patterns and with nets. If it actually will fold up for me once I get them all in place, how precise I need to be, but we're going to try it. Have one last triangle to move around to get back into the situation so it's in the net. And then if I select them all, let's see if it will fold for me. It may or may not. Nope, it doesn't like me because it's just not totally precise. So you need to be pretty precise if you're going to try to do that. But you can then see in there I was able to get it. So in order to get it back to build that shape. All right, and then the third one is a plan. So plans are a set of orthographic view of an object. So it's the front, the side, and the top view. It's used to describe an object to specific dimensions. So we're not going to dive into this too much, but plans or layouts are used so that one can construct something to specific dimensions. So this really gives you exact measurements so that you can then construct it. So a blueprint is an example for constructing a building. Plans are something that we use all sorts of places. So here's an example that we can see. So we see the side view, which is here in purple. So if we're looking directly at it from the side, it's going to look like this rectangle with a smaller rectangle at the bottom. And then we look at the front view. So we're looking dead on the front. We see that we have a vertical part of the rectangle and then a horizontal part of the rectangle at the bottom. And then if we look from the top, we see that we have a longer rectangle along the left side and a more of a square rectangle along the right side. So if we were to take those 3 pieces of information and put them together, we would end up seeing that this is actually what our shape is. It kind of looks like a chair sort of shape that has a bottom seat and then a back part of the thing. So an orthographic drawing is these 3 parts where you have side view, front view, top view, so that we can get this this image. Here's another example where we have a rectangle with a circle from the top view. From the front view, we see that we have that rectangle as like our base, and we have that circle. Well, it looks like a rectangle from the side is sitting on top of that. And then from the side view, we see that our rectangle is shorter, and we then have that again, that smaller rectangle is centered. So if we were just have one of these pieces of information, we wouldn't be able to picture what the whole thing is. But having 3 pieces of information means that we can then visualize that this rectangle base with a cylinder sitting on top of it, a smaller cylinder sitting on top of it. So that's what a plan is, that you can take those pieces of information. In theory, we'd have dimensions. I just didn't write the dimensions on here so that we could actually recreate these objects. All right, so there's only one support question on page 38 for this section. This is a very a smaller unit or smaller lesson. So if you want to pause the video now and look at that, that'd be great. And let's consolidate what we've connected and then sort of look at what kind of problems we might be dealing with. I did not animate this properly. Anyway, lesson 15 highlights, we're creating nets. So nets are a flat version of a 3D object that can be folded to create it. A pattern is a flat version of a 3D object with parts separated. A plan is a flat version of a 3D object that shows the front, the side, and the top views so it can be constructed. That's how they are different. So our success criteria is that we can visualize 3D objects and the nets that create them. We're going to practice that a little bit because it's definitely challenging. And our success criteria, second one, is that we can explain what makes a net, a pattern, and a plan. Hopefully you can do that now. All right, so let's do some practice problems in terms of figuring out how this is actually useful information. It's pretty different than what we've been doing so far. So number 1, this is part A. So draw a 3D diagram of a box with dimensions where the length is equal to 20 centimeters, the width is 8 centimeters, and the height is 30 centimeters. So a box is going to be a rectangular prism because it doesn't define it any other way. So we're just if you think about a box, it's like our faces are going to be squares or rectangles. So how I draw this, again, does not need to be perfect. I'm going to draw my front face. And so that's a rectangle. And then I'm going to draw it at an angle. I'm going to extend, I'm going to draw parallel lines back. I always do this where I draw my bottom one a little bit too far. This can be something that if you're doing it with a pencil, it might be a good idea if you want to practice a little bit, just because it is a little bit finicky. However, if you don't and you scribble things out, it's totally fine. I don't need this to be perfect. So then you can see roughly what that looks like. If I wanted to draw it transparent, then I would draw dotted lines to try to visualize that. Again, my line should be perfectly straight and everything should be parallel, and it's not, but that is fine. So I've drawn a 3D diagram of a box, and now I need to put the dimensions on. So the length, I'm going to say, is 20 centimeters. And this, let's just change colors so that we can sort of see what I'm talking about. So my length, I'm going to say, is this direction, is my 20 centimeters. My width is going to be sorry, I've lost my pen. Width is going to be this direction, how wide my box is, and that's 8 centimeters. And my height is going to be this direction, which is 30 centimeters. It is, so as you can see, my box is not drawn perfectly well. I wasn't taking that into account. So in theory, I could, now that I've thought about my dimensions, I could redraw my box and try to get it a little bit more precise in terms of the actual dimensions. I am not too picky about you having perfectly in scale lines, it's not that important to me because I think that knowing where the dimensions are is more important. But I'm trying to sort of do a little bit of a sketch now of what would make a little bit more sense in terms of the dimensions. It's really hard to do it to understand in terms of 3 dimensions, right? To see what of them, this perspective. I'm not a visual artist, so if you are a visual artist, that might make it a little bit easier for you in terms of knowing how long your line should be in order to make it visually make sense. But this box is a little bit more in perspective for what it should be. Again, it is fine if you don't have it perfect. I would accept both of these really if you have your measurements on it. That is fine for me. It's the right general shape, but nets are tricky to draw. Okay, so then part B, so use the 3D drawing to create a net of what the box would look like when it's unfolded, including the dimensions. So I'm going to draw a quick sketch again of that box that I just drew. As you can see, every time I draw my box, it is slightly different. I am okay with that. I remember the dimensions because I wrote it out a couple times. So my box is 8 centimeters wide, 30 centimeters tall, and 20 centimeters long. So now I'm going to draw this as a net. So this can be a little bit tricky to figure out how to unfold it. So I'm going to say, okay, I've got a big rectangle here. So I'm going to start with that face. So that rectangle I have. And doing this in colors could actually be really useful. Just going to see what colors I did last time so that I sort of consistent. So having color coding it could really make it a lot easier. So you don't have to color code it at all, but if you wanted to, you can, and that makes it easier to visualize what's going on and where your lines are going to be. As you can see, mine is getting pretty messy, but this is just the sort of the part that I'm working through in terms of being able to draw my net. This part is like my thinking opposed to what actually is the net that I'm drawing to communicate my information. And this is why it takes practice. Okay, so this is my face I have over here. I took this face and I sort of went it flat. So actually, I'm going to erase what I drew now that I have colors, and let's do it in color so that it's easier to see. So if I take this face and I lie it flat, I'm going to have 2 sides are my purple 30 centimeter sides. And then 2 sides, the other 2 sides are my red 20 centimeter sides. Okay. And then I'm going to think, okay, so now it's along the bottom. So I know that I'm going to have 20 centimeters is going to be one side, but now this side is going to be a 8 centimeter side. So then I'm going to end up with an 8 centimeter side, an 8 centimeter side, and then my other side is going to be a 30 centimeter side. If I was doing this by hand and not on a computer, I might use a ruler to make my life a little bit easier. I probably would, but here I don't have a ruler. So I am just doing it by freehand, and it's pretty awful, but hopefully you get the idea. So now I've done this side and the bottom, and now I need to do the other side that I can't see at all. And that's going to be the same as this side because it's a box. So that's going to be the same on both. So that's going to be another 30 centimeter side for that dimension, and then a 20 centimeter side to make it a rectangle. If you're just listening to this, it's going to be really, really hard to understand. Really, you need to see the visual to understand what's going on. And now I'm back to the top. So then I'm going to get another 8 centimeter, a rectangle that has 8 centimeters by 20 centimeters. So I found that having the colors really helped me to visualize it. That might not be for you, and that's totally fine. But that really helps me to know. So then 20 centimeters are all these red lines, and 8 centimeters are all the green lines, and 30 centimeters are all the purple lines. So now, are we finished? Have we drawn a full net? No, if I fold this back up, I'm just going to get the top and the 2 sides and the bottom. I'm not going to get the front and the back. So I need to figure out where the front and the back go. I'm going to attach them. Doesn't matter. You could attach them to either this one or this one. You could attach them to a couple of different places. You can decide. Again, I'm not going to be looking for exactly the same image. It's just as long as it makes sense. So the front, I'm saying this piece here is 8 centimeters by 30 centimeters. So it's going to come out here like this and have 8 centimeters is the other dimension. Be the front. And then the back would go here, 30 centimeters by 8 centimeters. And then I'm just going to label a couple of more sides. Again, because I color coded it, to me, it really seems very obvious which ones are the ones that are going to match and which ones are the same dimensions. But you could label more to make it make sense for you. And that's how we would create a net from this 3-dimensional box that we drew. That's what the net would roughly look like if it was a little bit more precise. So it takes a little bit of practice. It's definitely a little bit tricky. All right, so then number 2, sketch a pattern that can be used to cut out the pieces of a hoodie. Again, I'm not expecting perfection. I'm expecting you to sort of logically think about what a hoodie has. So a hoodie has a front, it's going to have a neck. And if you want to actually look at your hoodie, if you have a hoodie on, I do. So a hoodie generally has one front piece. So this would be the front. And one back piece. If I was actually, I'm sort of thinking about it in terms of the fabric once it's been cut. If this was actually done on paper to build it, they would do it slightly differently in order to save space. And then a hoodie is going to have a sleeve. So the sleeve, well, it's going to look kind of something like this. No, I'm doing it wrong. because I was then changed it in terms of, my bad, in terms of the piece of paper. Okay, a sleeve, if you were to actually cut your sleeve off of your hoodie and lay it out, it's going to end up looking like basically a big rectangle, because then you roll it up and you get the cylinder. And then, so this is a sleeve. Spelled it wrong, and you need 2 of those for 2 long sleeves. And then the hood would be, is kind of basically sort of like a semicircle, would be the hood. And that would be the pattern. If we put those together, in theory, we get a hoodie. Okay, so then 3, a bakery needs a new cylindrical package for their oatmeal cookies. Each cookie is 1 centimeter and has a diameter of 8 centimeters. Each package should hold a dozen cookies. Draw a net that can be used to make the package. Okay, so first let's think about, we have a cookie that is 1 centimeter tall and 8 centimeters wide in the diameter. So we're trying to figure out, we need to have a dozen, so a dozen is 12. So we want to stack 12 cookies on top of themselves so that we have enough room for all of our cookies. So our shape is going to look something kind of like that. Our package, because we want 12 centimeters, right? Because we have 12 cookies. So each is 1 centimeter thick. So it's going to be 12 centimeters tall, and it's going to have a circle with a diameter of 8 centimeters so that each cookie fits. We're assuming that it fits perfectly, even though that's not actually how the packages happen. We need to have a little bit of room for clearance, but we're just imagining that it fits exactly, and that's fine. So here for this shape, this is going to be, this is a cylinder. So we have our rectangular part, which is going to be, we unfold it, it's just a rectangle. Going back and playing with GeoBra can help you see that. And then, so that means, so I've taken this and I flatten it out. So this side is my 12 centimeter side. And then I'm going to have a circle at the top. It has a diameter of 8 centimeters, and a circle at the bottom. That's the bottom, is going to have a diameter of 8 centimeters. And that is the net for that. We could figure out the length of this if we needed to. We don't need to, but that would be this circumference. That's how you go around that circle that is the top. But that's not what we're doing at this point. That's all we need to do. So this is what the net would be would make that package. All right, so we covered a lot. We have a little bit of time, so we're just going to look at the support question. There's the one support question we're going to go into a little bit to help visualize what's going on. So we have a few more minutes left. So question 1 for your support question is, below are examples of nets. Which would produce closed objects? Explain why the others will not. So we can look at these and we can try to fold them. If you want, you can actually go into Polypad and you can make these shapes, some of these shapes. The ones that have the circles you can't make. I tried to figure out if there was a way to do it. You can't. But we could make this E shape we can do. So how you would do that is that you go to the polygons and find the shapes. So I'm going to get a rectangle. That's this rectangle. Then I'm going to get this rectangle, put it beside. And then I'm going to get this rectangle and put it beside. And then I need 2 triangles. So then I'm going to get a triangle and put it beside. You got to get it so that it's actually clicks in. You'll find it if you play with it. It sort of snaps to the objects. So now I've made this shape with my 3 rectangles and my 2 triangles. I'm looking at shape E. And then if I select them all together and I press fold net, if I click it, you can then see that it's now made a triangular prism. So E, you're able to make a closed object. So this is a closed object. There's no side that isn't closed. There's no way to get into that box when I'm turning it. If for say my picture was like this and I only had 1 triangle, I had 3 rectangles and 1 triangle. If I were to fold that net, we can now see that it is not a closed object. We can see on this one side, we can see inside of it. It's like a tunnel that, it's almost like a tent really, that has a back and no front. So that's not a closed object. So that's what it means when it says it's a closed object. So then the same thing we can do with B and A objects. So we can go back to Polypad, and again, I'll link this. So you can build those ones. You can see, okay, so A is a square with 4 triangles around it. So really, I find it easiest to actually do this opposed to visualizing. It's hard for me to visualize. It's easier for me to actually play and create it. Then we can fold it and we can see again, A turns into a closed object. It becomes a square-based pyramid and all the faces join and meet. So you can do that with A, B, and E. With C and D, you can't actually do that on Polypad because you can't actually get we don't have circles. I don't understand why, but they don't have circles, so we can't do that. But if you go to GeoBra, which will have linked, we can see that, well, D is very similar to the net of a cylinder. It actually is the net of a cylinder. These circcircles can be placed anywhere along this long line, this side of the rectangle, so it doesn't matter that in the example that I'm showing it is centered. And in the D example in the support question, it's all at the top. It doesn't matter. So we can actually fold that, and that's going to make a cylinder that's a closed object. Here we see it. It's transparent, so it doesn't look like it's closed, but it's a closed object. It's just that it's transparent. in order to see the circle along the bottom. That's just how GeoRep plays with it. C is the one that, according to the support questions, is not would not be a closed object. I struggle with that because I look at the net of a cone. To me, it looks like it's going to be a cone. We have a circle, and then we have this arch. And I feel like if I were to fold this and make a cone, kind of like a cupcake, or sorry, an ice cream cone, if I would join those two sides together, that it would work as a cone. So I would disagree with what these answers in the back of the booklet say, because they say that C can be a closed object. I don't know if it's just because of the dimensions, but they don't give us any dimensions, so I can't guarantee that you're going to have a hole or anywhere. But to me, I think that that is a net. If they were to put this circle on one straight lines, then it wouldn't be a net because we wouldn't be able to fold it into be a cone. The circle needs to be along the curve, but the circle is on C along the curve. So I don't understand where they're coming from. For the folks who wrote the booklet, it was not me. So in future classes, I will adjust that to make that make sense to me and hopefully to you. Okay, so that's the support question. That's the only support question in this unit. So there are only, or in this lesson, there's only a few key questions to do. So dive in. Again, I would really strongly suggest playing with those two websites that I'm going to share that we use today to really understand, to be able to play with it. It's really hard to visualize. And ask me questions. We can chat about how to make these nets make sense if they're not. As always, please contact me if you have any questions or anything isn't making sense. My phone number is 807-737-1488 or 1-800-667-3703. You can leave a message for me there at the main desk, and I will get back to you as soon as I can. I will call you back. If you want to tell me when's a good time to call you, that's great. I will try it so that we don't continue to play phone tag. Emailing me is a little bit more reliable to get directly to me, which is bronwyn.slate, spelled BRONWYN.SLATE @nnec.on.ca. And connecting with me through Facebook is also very reliable. I get back to that very quickly, where my name is B. Slate Wahsa. This lesson will be uploaded this afternoon on YouTube at B. Slate Wahsa. And so you can review it back and then also have access to the show notes and the notes on YouTube, just so you can click through and find the links to those places where you can go and play around with those different manipulatives and make it make sense. I hope you have a lovely day. Thank you for joining me. Miigwech.